Okay, everybody there on his place? Yes, perfect. Thank you for coming. I think I can start and everything is fine with the sound. So the talk will be about unlocking performance through reverse engineering. My name is Patrick. I'm not going to pronounce my last name in English because that always comes out wrong. I'm a principal CPU architect at Ascenium, and I will give a talk about reverse engineering. Reverse engineering. So we're going to reverse engineer this laptop, this core, this CPU core, and I will start with some examples, and we make it a bit more difficult, and then we talk about it, what we can do with it. So this talk is also a reverse talk. First examples, then what we can do with it, and then I will tell you why this can be interesting and even more in the future. So everything is upside down. Hopefully that works. So what we want to know, for example, the most thing what I want to know is that what is the speed limit of our CPU car? How fast can it drive? How fast can it go without taking any turns, any branches, anything? We just can press the pedal and what happens? Yeah, so that's what we were going to find out with the first macro benchmark that I will try to set up. And therefore, but maybe first we try to find out which CPU core actually is in this core. Yeah. So let's see about that. We can, if we do like this. Grep model. This is an Intel Core Ultra 7 155U. That doesn't say so much, but if you look at here on the website of the Intel Core, you can find out we have Meteor Lake core, formerly known. There's 12 cores, 2 performance cores, and 8 efficient cores, and 2 low power efficient cores. So we want to focus today on one of those performance cores. And how do we find this out? We can run another lscpu command. Here, these are logical CPUs here actually. So we have here 14 as they have described. So which ones are the performance cores? The performance cores, they can have 2 threads. So if you see here, the same, if you have 2 CPUs, so this thread here, or this CPU, logical CPU 0, 1, goes to the same core. These have 2 threads. This one 2, 2 and 3, these have also 2 threads, and all the rest have only 1 single thread. And you can also see it on the max speed. These 4 here can run on max speed, while these are lower speed, which was here a bit down in the thing. So this is good to know for afterwards, because we want to set the program that we are benchmarking on the correct CPU. So we will use CPU 2, which is on the performance core. Okay. I'm switching a bit screens all the time, but hopefully that works. So how do we measure the speed limit of the CPU core? Well, therefore, I love doing nothing, or at least telling the computer doing nothing, this core doing nothing. Like I said before, we're just going to do everything and see what happens. So in order to do that, we have set up Google Micro Benchmark. Actually, many of them, yeah, but you will see in a bit. I just try to walk through this code. We have here a function, a benchmarking function. I called it 2 because we have assembly that says execute 2 no ops, and we use volatile. to make sure that the compiler doesn't throw it away on the way. So this is just to build up on how this function is used. So I love no-ops again. So then we have another function, benchmarking function that will, or micro benchmark, that will say 3 knobs. So that's why I want to know. So what we want to know now is how many. I want to send as many as possible through the computer, through the CPU, through this core. Except I don't want to write, I'm lazy, I don't want to write all these separate benchmarking things and then gather the data. So I made this in a template where here we have a statement rept that says how many times this knob needs to be repeated until here. So basically, whenever I could have replicated this one, 3, with saying here 3, but now this comes from this increment or from this in, which is our template. And we just create many knobs. Exactly in here. Normally you need to register in Google Benchmark every benchmark, but we make define that it's expanded through this include file, which I have here. Here you can see we have hundreds of numbers that we will use to register benchmark max throughput 1 for 1 knob, 2 knob, 3 knob, 4 knob, 5 knob, 7 knob, etc. We do this for 10 repetitions, where we take the average for, so we know more. We have kind of stable results, and we report not the aggregates only because I like to have the raw data and to play with it. Is this clear more or less how this benchmarks is set up? Yeah? Okay. Then I need to go to my other screen. Okay, first we need to build it. We're using Bazel. Hope you're all fans of Bazel. No. I have some. I saw some talks of wars from Bazel, or yeah. So we'll look at that also. So let's. I think for now it works. Yeah. So. Now I lost my thread a bit. Yes, let's say this. Okay, let's build it. Okay, now we have it. Now we run it. There are too many flags, so I use this fuzzy finding, which is yeah, very helpful. Okay, here. Okay, it starts. I'm going to stop it. I have the data. So, but because this data we can put in a JSON or a CSV and we can count iterations. So, but why this is? So, do you know now how fast the CPU is or not? Yeah. What is our maximum speed? We don't really know. Also because we get this warning, the CPU is scaling up and down these measurements of time, how long things take and how many iterations. That's varying too much. Yeah, so that's why I like to abstract that a bit and actually look at cycles. So the speed limit, the speed is how many instructions can we do per cycle. Is instead of the speed limit, instead of how much time does it take to do one iteration. So, but in order to do that, we need to some of the things we need to compile it with performance perf module. So you can get the performance counters out, instructions, cycles, and support. And we add this. Yeah. Okay, that works. And what we can do then is so we set the CPU to 2, which we found out in the beginning. C2. We run our benchmark, but with performance counters, cycles, and instructions. They come from perf, from the performance monitoring counters in the hardware, and they're quite accurate. So here we go again. And the other things are just to put it in a nice table and color it. So, yeah. Which one? Ah. Yeah, it is to be able to add the performance counters. Like these counters. If we don't do that, then we can't do this. Yeah, yeah, that's from Google benchmark. Yeah, they add this lip4f. Yeah, forgot now but there's a library that's added. Yeah, but good question. Yeah, so here we forget about the first 3 columns, but here we get the cycles and instructions. Here you see also this is 0 is the n that we have done. So I also have put n is 0. Why did we do that? To see how many to see what is actually how many instructions we do when we don't add any no ops. Yeah. Here there is 1. Now the number of instructions increase because we have 1 extra no op or nop. And so forth, and then this goes on for 100 iterations. So yeah, okay. And then to know the speed, what we do, we divide the instructions, the number of instructions, by the cycles. So, like I said, I did some work for you, and I have here the maximum throughput of my CPU core. So what do you notice? Yeah.
So that's your average, and in the beginning it's really low, so probably because this tool has something.
Yeah, correct. So in the beginning, and for some other reason too, but you have 7 instructions here. Almost, yeah, 7 instructions, and then it goes down to 6. So why is that? It's also because the short peak of 7, and then now I took the object dump, and as you said correctly, these 2 extra instructions that are counted in the beginning, even with null ops, it's this branch. So here this is a counter for the iteration. It's subtracted every time, and when this is 0 or not 0, it jumps to here again. That's a branch and jumps to here, and then we do the next iteration and so forth. And we're counting these 2 instructions. Now, this is these 2 instructions. There's something happening inside the CPU with it, inside the core. They are collapsed into 1 micro operation. So some of them are micro. That's why we see here that once you have enough instructions, it doesn't matter anymore. Yeah, that's why you get 6. So, but in the beginning, with only a few instructions here, you see these extra instructions, and it seems like you have 7 instructions per cycle. Okay, but in order to counter that, we would look. I would like to look at the micro ops. Wait, okay. So let's see. No. So you have an event that's called microops uops issued.any, which we can also try to get from for our benchmark later on. I'll just show it. Yeah, so here we just sleep. Actually, we need a task set before, because otherwise we don't get to the CPU core. Yeah, so many, just sleeping takes so many things. So what happens is, so your binary is read, your things are decoded, all your instructions, but before it's given to the backend for execution, there's some instructions that are collapsed or splitted. Okay, yeah, and that's what we're counting now. So how many microops are coming from the front end to the back end? Except there's one slight little problem. If I want to use it here, like this, it says unknown performance counter. Now we all can go home, which I did last year because I had the same problem. So we don't get this counter that actually measures the X speeds, but at least you can get it in perf with the performance monitoring, but not through benchmarking. How can we resolve that? We go to the perfmon events Intel website. We go to our Meteor Lake core, and we can look it up, and we have it here. What we will do then is use this event selector, AE, it's hexadecimal, so and 1 in hexadecimal. And now we need to do some operation, which I will show you. If everything is fine, it comes here. So we have the event selection, and the umask acts like a filter. So what we need to do is to shift it by 8 to the left, the binary, hop. Oh. Then we put this in binary from hex to binary, and then we do a bitwise OR, is basically collapsing them together. We get this number, and then we can use R for raw counter on perf, 01 AE, or R1 AE, because it doesn't look at the thing. Okay, and then we get our microops. To show that this is the right one, can do like this. R1 AE, was it right? Yeah. Exactly the same number. So I can do it again. So now, are we confident that this measures what it measures? Yeah? Okay, good. Okay, back to, we do now do, so instead of this, we do like, Here you are. So here you see 2 instructions, but only 1 micro op. Correct? Yeah, that's what we had found before. And then this is already the next slide. Yeah. Okay. So and then the maximum throughput is 6 on average. So now we are doing 6 micro ops, and that's in a way the real bound on your speed of your of the core of this Meteor Lake performance core. Okay. Yeah. Before we continue, more questions about the setup or something else? No? Then I proceed. Yeah. So of course, how well you over.
If to the end, maybe I'm just looking at it. To the end, it looks like it's dropping down to a maximum of 5.9 or something.
Yeah. True. I have yet to find out. Yeah, but this is true. I think with more operation, with more I did with more repetitions, but then it takes very long. You see it kind of having it less. Yeah, but that's a good question. Yeah. Yeah. No. That's a good question. I can show you maybe the object dump. So here is the object dump for 3, I think. Yeah. So here it just has nope, and then these 2, and then it jumps to here again. So there's no repetition. It's not something that's in the binary or in the code. It just it's a way to express what you want from the sample. Yeah. Let's do. That. Is it now here? Here you have 10. So you see it growing, the number. Yeah? Does that answer the question? Yeah? Okay, great. It's good. Good. I like questions along the way. Hopefully I have enough time, but I like it. Yeah. So where was I? So how your program performs or how fast it is doesn't only depend on your microarchitecture, on your CPU. It also depends on your program, on your workload that you're offering. So what is the most important thing, of one of the most important things that a core does to try to be at their max given the workload and the microarchitecture is the following, and this will lead to a hardware structure that we will reverse engineer that helps to try to get the max as close as possible to this max speed. So I have a small I don't know whether this is a useful function, but it fitted on 2 columns, and I also had the assembly in 2 columns, so I was happy with that. So it multiplies, does an addition, and so and subtracts in the end and puts it back in a memory location. So just to give a relationship between the C code and the assembly code. Here you have the parameter A. It's in EDX register. Parameter B is in the ECX register. Then we have a load of X. We have a load of Y there. Then this is the address where we will store it. Then we add what we load and the parameter A. The result is stored in EDX. Then we multiply what we have loaded from Y by B. Then the result is stored in ECX. And then we subtract EDX and ECX. And then we store it here again. Yeah? Okay. So what happens in practice when things are issued in micro ops, in micro operations? then so there's not only fusing going on, there's also splitting going on. Yeah, so you want to, sometimes they want to split this add and this multiplication into a separate load, or separate loads and a separate logic execution, like an addition or a multiplication, because then it can be treated separately in your CPU core. So it's not only fusing, what we have seen with the branching and the subtracting, but it's also splitting, because then it can go different ways, one to the memory and one to the thing. Yeah. So here this is a bit made up notation. We don't actually know how they encode it. So I just used R1 and R2 instead of ECX and ADX, but it are physical registers, and you have more physical registers in your CPU, much more than what you have in what you can express through the architecture. So what does, let's suppose we are doing this in order. We're executing this assembly in order. We can do this load here, but often the first load, what happens with it? Waits for the data. 20 cycles. If it misses all the caches actually on this computer, it will be about 200 cycles. So it waits a long time. So it stalls on this one. It can't execute this. What happens if what this CPU is doing, of all modern CPUs that wants to try to get as much performance out, most of them, they will do the load. There is again a cache miss, but they can continue. And they continue and they return when R1 is ready. So this one they can't do, but they can do this. They can start another load and it's overlapping. And then execute the multiply that they can do, which is also a long operation, etc. So you see it goes beyond this stall. It starts executing things it can do. That's why you have an out of order backend. So out of order improves or tries to get to the max speed by overlapping execution of long latency operations. That can be multiplications, loads, stores, etc. Yeah. So what we, second thing that they do, so here just a schematic picture from the front end. We have these micro-ops that go to the back end, and here they do it out of order. It also does branch speculation. In most of the workloads that you see, every 7th instruction is a branch, and we can't, if you wait for every branch to know the value of it to where to go, then you will also stall a lot. So what happens, it does branch speculation, and for every branch at the end of a basic block, it will try to it will try to speculate, should we go here or here? And in this case we go left. And in this case we go left again, and then to the right, etc. And we don't go to here. Or actually this was a wrong thing. We might take this one to the wrong path, while actually the green ones are the correct path. Sorry, that's wrong of me. But we discover here a wrong prediction. That means that we need to be able to roll back and go back to this branch and execute things again. And we try to do that as little as possible, or at least the CPU, not me. But we need to keep some state that makes it that we can roll back, and also that we don't say that instructions are retired before they actually, we know that they were part of the program. Same thing with an exception. An exception we also need to handle in the same way. So, and now we come to the hardware structure. Yeah, that we will try to reverse engineer. This is the reorder buffer. So the reorder buffer is a structure that keeps all the micro operations that come in here in order. This is their order number, 1, 2, 3, 4, 5, 6, many more, as we will see. But you can only retire this first micro-op or instruction that's related with it when you know this is speculative, and everything, when you know that this was part of the program and not speculative. This one too. So you can only retire this one before you can retire this one and say this is done. Okay, this is clear. No, you want to ask about it? Yeah. Yeah, that's a good question. So a retired instruction is an instruction that's executed, and you can retire them because you know it was not on the speculative path that you have taken in your order. So you know it was on the correct path and that it should have executed. And then you can retire it. That means that the CPU can doesn't need to think about it anymore. It's gone from the reorder buffer. Other instructions can be part of the, yeah. Yeah, both will appear on this buffer, but as soon as it detects that it was not good to try to execute this, it will roll back this buffer and try to get to the wrong right path again. So it will remove them. Yeah, and then they're not retired, they're just thrown away. That's called flushing the pipeline. Of yeah, okay, yeah.
So these microbes in the buffer, then they're kind of what we speculate will happen.
Yeah, what we speculate will happen. Yeah. But not what we speculate will happen, but at some point you know they actually needed to happen. So, and then they're green. And you can only retire things that are green if everything else above are green. So that's why it tries to fill up until it actually knows the data and knows that you were correct. So when all the branches are resolved. Yeah, okay. So this is a very important structure because the bigger it is, the further it can look for independent instructions to execute. So in the beginning of when 20 years ago, they were much smaller. So your program cannot find so many independent instructions as here, yeah, or if you have bigger programs. Yeah. So this is very important to improve the performance, and every hardware structure is kind of balanced with the size of this reorder buffer, because this keeps everything intact and make sure that you in the end have a correct result and not a speculative result. Yeah, like a result that's wrong because you happen to follow the wrong path. So what's the size of this reorder buffer? So how far can we find, and how do we find out? We can find it out by, again, using knobs, no operations, but again, we do a load first, a load first, and another independent load here. And I'll show you a bit how this works with some drawings, and hopefully that will explain the code well enough so that it's clear what's happening in the code. Okay, so we have this. These are the steps. First, decode, execute, retire. Retire, you don't need to think about thing. We assume now nothing is speculative, everything is correct. So you have a load, a long latency loads are gray, you have no ops are green, and the loads, second load, independent load is red. The decode, here it's decoded, it goes quite fast. That's here of the first load, this small little gray area. Then it, after it's been decoded and put in the reorder buffer, it can be executed. This case 200 cycles, more or less. Then the no ops come in. Here, boom, 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 boom. Depending on how many they are, they will grow or not. This green part, no ops are actually not executed, and they can be retired after this one has been executed and deemed to be not speculative. So here you see a gray one. Same for load 2. Here it comes behind, because that was the program order. Load 2 is here. And this is in a way the order in the reorder buffer. Here it was decoded. It can be executed, let's say rather immediately, back 200 cycles. And then we can retire it here. So in total, it takes about 250 cycles on this drawing. So what happens if we add so many knobs that the reorder buffer is full? The second load can't start because everything is held back by this first load. Yeah. So you have the first load back decoded, you have all the knobs, but you put so many knobs into this reorder buffer that this second load can't be added. Your CPU will stall. Yeah. We can ask the hardware engineers that, yeah. But this is how this hardware structure works, yeah. So you need to wait. I think normally you don't have knobs. Normally you have things that are executed, yeah. So yeah, true, but you don't know whether. So this was a non-speculative case, but you didn't know whether this first load was maybe part of a speculative path. So you need to wait until you know. In a real program, you need to wait until that load is known. Yeah, known in the branches before, and that's why it needs to stay, because the reorder buffer needs to retire things in order. In a way, I always think this name is a bit weird. It enables reordering of the instructions before, but it actually wants to keep the order, yeah, of the buffer. So I would almost say it's an in-order buffer, yeah. So that's maybe that helps with understanding, yeah. But I think the comment of the person sitting on the second row was correct. Is that if the rope is full, we can't put it in because there's no place, and then the whole CPU will stop. And you need to wait until this is executed and this is retired. So the first load, and then you can put it in. And then you have this load here. So it means there's no overlap, even though it are independent loads. So in a way, reverse engineering is in a way really the opposite. We try to find out when the performance goes really bad, because then we know how the sizes of this hardware structure, we can do other things about the sizes of this hardware structure. So, and this is about 400 nodes. Yeah, okay, and then, but I have drawn now very 200 cycle loads, but what happens if it hits the cache directly and you have 4 cycles or 10 cycles, yeah. Then what happens is these loads come very fast back. They can retire. And also here the knobs, like in your case, can already start retiring because that came back. So it means that the rope never gets full. So we need, for our test to work, we need to have independent memory loads because you won't have overlap. You should be able to execute them without depending on data from each other. We want them to miss caches, like all the caches, because we won't have these 200 cycles. We need to be able to load somehow in random access order because these hardware prefetchers get smarter and smarter. So we really want to, we can't just do memory loads and just go from one place to another, because in a very structural way, because that the hardware prefetchers will catch and they will put it in the cache before we know it. So you get different things. And we want to have a minimal extra instructions, so it just keeps counting all our micro ops a bit easy. So we don't want to, we like to have as plain as possible load, knobs, load. So and what can help us with that is a random cyclic permutations to the rescue. So what we want to build is, if you look at these are the indexes, and here are the is the array, and the value. Maybe I take the value in this array for this specific index tells us where to go afterwards. You will see why this is useful later. And this this I draw a bit wrong, because the 8, so if you are here, the 8 should be going here, not here. So my mistake. Yeah. And then the 5 should go to 5 here, etc. Yeah. But so you want to have a large one single cycle, and we want to randomize that to let's suppose that here it goes to 0 again already. Here, then we have then we will not have one single big cycle around these permutations. Then we will go back to the same place, and that will, for sure, the hardware fetchers will detect that. So we want to have one big single cycle through a large memory space. Like this one, this is, if you follow the arrows, it's one big single cycle from 0 to 8, 5, 4, 7, 9, 6, 1, 3, 2, and I'm back to 0, and then we can move around. Now imagine that this is our memory, and in this memory location you always know then the address where to go next. So we get like a pointer chasing example. So we can do pointer chasing. And how do we get our independent operations then? Our independent moves. We just split it up and we choose at random a starting point within this cycle, which we will use to move forward. So this will be our first load, and this will be our second load, and in between we will have knobs. And if we make this memory big enough, like a huge page in memory, then we have a very little chance to kind of get into the cache. Yeah, so which we wanted to avoid. There is one algorithm that is called Satoru's algorithm, which kind of builds up this one single cycle, and it can generate with equal chance every possible permutation of such something. It does it by taking a cycle and then start. Everything is one cycle, and it starts on the left or on the right. You can choose, and then you kind of expand the cycle every time with a random position where you need to go next. And what is important is this is y plus 1, because you want the not choose itself, otherwise you have an individual cycle in this thing, and you basically go do the same. Okay? Oh, too fast. Yeah. So hopefully this code now is kind of more comprehensible, but it works. So the same benchmark type of thing. We use the same n in this registration here to get to the ROP size. But what here is the move. The move is in this case a load. MOF, I don't know how to MOF. Yeah. So this tells us, yeah, get to the memory, load this 0, percentage 0. That's a register. In that register, there is the next address location, because you have this pointer chasing. You load that one and put the value back into the same register. So that's why we get this pointer chasing, and you just get. So we have here our load, the same here. We have our no operations, and again, another load from the other starting point. Why do we choose other starting points? Because if they're far enough each other, probably because if it's very big, then they're independent loads, and we can just, yeah, they don't interfere and we can overlap. Yeah, so do you see the structure? What I here, back, load, knobs, load. Yeah. Then we can do run it again. I can compile it again, but it's already compiled by Basil. So we can just run back. Yeah. I also have some timing thing I need to watch out for. Okay, here it goes. You have 5 instructions. 4 is a bit the same. You have some variation here. I think that there is just statistics also. Sometimes you're unlucky or lucky. Or yeah. So let's see. I made a graph again. Maybe you saw it very fast. But here it is. So do you have an idea around which here are the number of instructions around no-ops, and here is the cycles. Also notice that it's quite close to what I predicted in these pictures. And now I saw it. Yeah. The ROP size is you have to believe it just took a bit more out-zoom picture because you see it then better that it jumps a lot. Yeah. So but the ROP size of this is 512. So it can look 512 micro ops up front to find independent instructions. And we did all this by just making a small micro benchmark, and we can do this programmatically to get into the next. Yeah. Of questions. Yeah. 10,000. Yeah, a lot. Yeah. I forgot now which one I used, but yeah. It needs to basically just the whole a huge page in memory. There were 2. I don't know who was first. Yeah. I think more repetitions and taking the minimum instead of the average will flatten that out. I think it's just noise, but it might be something that we don't understand yet. This is no. You know it. I think you know it. Yeah, you can know it on the. I think if Intel publishes its new core, I think they say it. Yeah, I don't think it's really mentioned in the documentation how many they have. So yeah, I need to check. But it's also the reason why I show this. Even this can be documented is because all the techniques to get the size of these hardware structures is a bit the same. So you just need to get to the thing, and this is just an important thing to know from the what an modern out of order PC does. Yeah. Okay. We proceed. I have I need to go a bit through it a bit faster, but here I draw a picture from the front end. You have micro ops. You have the back end. You have the physical register file. This ROB is the ROPS, is the reorder buffer or in order buffer, if we can use it for now. You have some schedulers that where the micro ops go to that checks when data is ready and then puts it to the right execution units. Now memory is handled a bit differently. You have they have often their own schedulers, and you have different paths for stores and different for loads, for address calculation and for getting the data back. And between that, the issuing happens in the store and the load buffer before it goes. So there is a store and load buffer before it goes to memory. Why is that? It's because basically the same is they don't want to wait until the store has done its work. That can take a lot of cycles. So you put the store and the value and the address in that buffer, and when a load comes, that goes for the same address, and you have the value of that store, it will do store to load forwarding, etc. And so, and the stores only are drained after. Yeah. Afterwards. Yeah. So after things that they. When are the Yeah, when the store is retired from the thing. Yeah, actually, a very good talk on memory models. Yeah, about that can help is actually from Anders, which you can see again. Yeah, that was my words again. A bit. Okay, but this load and store buffer is quite important. So how would we try to fill it up now? You have time until now. So here, so what do you see? What was different? Maybe I can. Oh. So what is different is that you have the load here still. That's still there. This still here, except instead of the no ops, we do a load here. So we fill up with loads. Right? And we do the same exercise again. Yeah? So now, since we're running a bit out of time, you just have to trust me. You do the same thing, you run the thing, and you get it. So, and we can do that for the store. You do the same, except here you have a store to this address. Just normal store, that's fast enough. So you fill up the store buffer as fast as possible. Yeah. And here the load buffer size of this one is 192. And this one with the same experiments is 114. So a bit less.
Can you show 142 active loads at the same time?
192 active loads at the same time. Yeah, yeah, exactly. And 114 stores at the same time. Yeah.
You parallelize the loads and everything.
Yeah, yeah. So you can overlap and wait, and they come also not back in order. Also not. Yeah, some hit the cache and some not. So, yeah. So now a bit the same thing. So here in memory on this part here, you also have another structure. It's called the what's it called again? The mishandling architecture. What's important there? There is also a kind of a hardware structure that keeps all the cache misses. So if you're missing cache, they say, we're missing cache. Okay, I need to wait. I put this thing that's disloaded here. You put it here, put it here, you put it here until it waits. So it's kind of the interface between the caches and the store and the load buffers. And this also has a maximum size or a size, yeah, which we can find out. And we do that by doing a similar thing that we done here. Instead of making 2 random starts, we try to find 1 pointer chasing, 2, 3 random, 4 random, 5 random, and they follow their becoming dependency chains. And from the moment they start, this buffer start to fill up, we can't start overlapping these independent chains anymore that are independent in memory. So that means that we will see stalling, or the speed of will not be linear anymore. So here you see, so this linear line is when what would happen if all this every time all these 25 loads, yeah, in this case it's 25, all this number of lanes can just go and miss the cache, etc. And then when there is no kind of bottleneck in this hardware structure. So if they can keep on overlapping, then you would expect this orange line to just go over it, and we can have 35 cache misses, no problem. They're just overlapping. It takes a bit more time, etc. So here in the beginning, you see it follows the same speed up, the theoretical speed up, when there is perfect overlapping of these cache misses. But at some point, it goes to the right, so it stalls, and it's about 25 number of lanes where it stops following the theoretical speedup where everything can be overlapping cache misses. So it means that we, in this CPU, we only can have 25 cache misses at the same time. Overlapping, then otherwise it stalls. So that means, you said before, we have 192 loads, more or less. So I think Intel, in this case, is expecting about 15% of these loads that are alive is missing the L1 cache because of 25 divided by, more or less. Yeah, maybe it's a bit less than, yeah, between 10 and 15%. Yeah. No, it doesn't depend on the lithography. It depends on the design of the hardware chip. Yeah. And the logic behind it and how big the structures will be. So that they know before the lithography. Yeah, putting it on. Okay, I see that yeah. Yeah, exactly. Yeah, I think so. Yeah. Huh? Yeah, but they need to do that, otherwise they can't overlap the cache. So overlapping of instructions is very important for your performance. Yeah. So that's what they try to do. But it's very difficult, even with the number of transistors, to get all these hardware structures working well together and make them bigger, because you need more read and write ports to that, and that takes more wires, and how do you fit everything in the chip? So and it also takes power. But I think I need to maybe have 5 minutes or something like that, need to get a bit more through it. But so now we have seen one way, mostly I focused on what is the idea on how to do getting the hardware structure sizes of it, but you can also do the latency of the operations, which ports it uses, on which execution ports. You can also do more behavior analysis on the branch prediction and so forth. So I think you're able to model with reverse engineering the whole CPU if you really want to, and people have also done this. They have, for example, Abo, a very interesting paper. They're characterizing latency and throughput of all the instructions. They do this automatically from the ISA. They have a more precise definition of latency because they take into account which type of operands they have in each instruction. And they get also machine readable output used by the compiler. And when you compare them with vendor tools, they are more accurate. Yeah, so that's actually very interesting. And also you can almost directly use it for instruction selection, ordering, and scheduling. And what is very fun is this one, for example. This is based on this paper. You can get it some here, some loop code, some things, some instructions. You can tell, it's Skylake now in this case. Let's run this. Then you get this. But you can even open up a trace to start understanding in which phase everything is going. This is very helpful to understand how your program is running. So they're modeling this in a very detailed way. Yeah. So another thing, for example, branch predictors, that is really something that's undocumented, because that's undocumented. That's the bread and the butter. People have reverse engineered this for Apple and Qualcomm. They've built accurate conditional branch prediction models, and they discovered effects that even the engineers of Apple and Qualcomm didn't tell about, didn't find out. And they just by, for example, in a simple binary search example, they added and I said I love no-ops. They added one no-op at the right place, and they could improve 7% of the performance of this binary search, which is like, yeah, quite important. So if you look at this paper, this is in the sources of this thing. This is quite incredible that by modeling and viewing on how this all works, that you can actually get so much information to improve your thing. And they also did some suggestions to hardware designers to reduce the second effect, and also actually told what to focus on later on in their hardware design. So it's not only useful for design. Okay, and then maybe the in 3 minutes. I can't explain this on time in the time that I have, but you can also improve directly work stealing algorithm. Work stealing by it's to kind of balancing jobs across multiple threads. Normally you need to do this with fences, because you want the victims, or where you put you want that the stores are seen by the other thread on time. So normally you would then kind of drain everything so that the stores can be seen by those thread, but this is not so that's why you need fences. But we know now, and it's not cheap to lock, so fences are not cheap. Yeah, so this I don't have time now to explain this thing, but basically it wants to say about 25% of the time you spend on locking on your program on these fences. But we know there is a bound on how much stores can be reordered with the loads, because we have the store and the load buffer sizes. And using that, you can make fence-free work stealing algorithms. And the performance gain was 7 to 11%, and on average up to 23%. So basically, by in your program, trying to detect the store buffer size of your computer that you're running on, and then try to make sure that you don't need to have fences in this algorithm. So what can we now do with this newfound ability? We can performance modeling and use the gained insights. We make visualizations of it, but we can also use these numbers directly to improve your program. That's what this was all about. And why we need to do that? Why do we, now I come to the motivation. Why do we need to do that? In the beginning, Richard Feynman said, yeah, there is plenty of room to improve at the bottom. I mean, at the hardware, we can do faster things. But nowadays, this is, even though we have more transistors, single thread performance is kind of in decline, and we really want to improve that. That means that we need to get to know our hardware more intimately and really going into software engineering, where we know more about the hardware. If we want to improve performance of our workloads, we have a bit less, too little focus on that in the last years. So where is there still some room to improve is basically also tailoring software to these hardware features. I'm sorry I was a bit over time, but that's okay. So I'd like to thank you for listening. If there is no other questions, I forgot about the conclusions, but you can just read it. Yeah.
Where would you put like the responsibility of this of trying to introspect on the device that you're running on? Would this be more of a compiler type thing, where the compiler should think about it as it's compiling your program, or is this more something that you could have as a meta program around your program to introspect on